Today's lesson is part 2 of logarithmic functions. We learned last time that log functions are just the inverse of exponential functions. So that's how we can solve problems that we have not been able to solve before other than by graphing the two equations and finding the solution that way. So very exciting times. Today we're going to graph some logarithmic functions. So here we go. Here's our standard form equation, and I want you to know that the a, h, and k do exactly the same things that they've done in all of our transformation graphing, so nothing new there. Remember, a is going to be a vertical stretch or compression, h will be a horizontal shift, and k will be a vertical shift. So here we go. If our base is greater than 1, the log base b, if that's greater than 1, then the graph is going to increase slowly. And if the base is between 0 and 1, then it will decrease slowly. And in the case in graphing a log function, we'll have a vertical asymptote. Remember, the exponential functions have horizontal asymptotes. The log functions have a vertical asymptote, and of course that will be the line x equals h. So let's just go ahead and graph a simple one, log base 2 of x. Let's go ahead and put our vertical asymptote in, right? H is 0 here, plus log base 2 of x plus 0. So let's go ahead and sketch our x equals 0 asymptote in here. X equals 0. And now, what I like to do here, because these are a little bit harder for me to do in my head than, let's say, the exponential functions or some other type, I'm going to make a little table here so I can get a few values. And what I am going to do is I'm going to rewrite my log equation in exponential form. And remember, that's going to read 2 to the y equals x. So what makes this special in this case is that y is our independent variable. So we're going to pick values of y and then figure out what x is. So I don't know, let's start with negative 2. If y is negative 2, then x will be a fourth. Now remember, our x values cannot go negative. You cannot take the log of with any base of a negative number, but remember this is y is negative. Okay, so negative 1 would give us a half. 0, 2 to the 0 is 1. Anything to the 0 is 1. 1 would give us 2, and 2 would give us 4. I guess I could put 3 in there. 2 cubed is 8. So let's just graph these points. So x is 1/4 negative 2, 1/2 negative 1, 1 0, 2 1, 4 2, and 8 3. So there's what our graph of log base 2 of x looks like. And of course, it's getting closer and closer and closer to the asymptote x equals 0, but we'll never get there. All right, so let's do one. Now this type B is between 0 and 1, so we know it's going to decrease slowly from above. So again, let's rewrite this in exponential form. 1/3 to the y equals x. Let's make our table. All right, let's pick negative 2 for y. That's going to give us 9. That may be too big. So negative 1 would give us 3. 0 would give us 1. 1 would give us a third. And that's probably about what we'll squeeze in there. So my graph, let me go ahead and put my asymptote in there. I like to do that first. Again, h is 0 here. So vertical asymptote right there at x equals 0. It's a good idea to label it. Now we got 9. We don't go that far, but I'll kind of guess at it. Negative 2. That'd be about right there, I guess. And 3, negative 1. 1, 0. And 1/3, 1. So our graph here with the base between 0 and 1 looks like so. And I should label this y equals log base a third of x, and this one is y equals log base 2 of x. So you can see the difference there, what changing the base does to the look of the graph of the function. Okay, now let's add a, h, and k. We're going to do the very same things that we've always done with a, h, and k, as I said. So first we want to identify our parent function, and we know that it is going to be f of x equals the log base 2 of x. All right, our vertical asymptote, remember, is x equals h. What is h here? It's 2. So we're going to have a vertical, I'm sorry, that's k. I take that back. X is 3. H is negative 3, right? Because remember, this is x minus h. So for this to be positive 3, h has to be negative 3. Finally got that right. All right, so let's put that in first thing, negative 3. Okay, and then what else is going on here? Okay, we're gonna go left 3, k is plus 2, so we're gonna shift. Let's put some parent function points in here. Log base 2 of x. Remember what we had here? This is our parent function, log base 2 of x. So I had 1/2 negative 1, 1, 0, 4, 2, and 8, 3. So there's my parent function. So now, what am I going to do? Let's see. It doesn't ask me to say what my transformations are, but I'm going to jot them down over here. Right? The negative a means I have to reflect over the x-axis. And I'm going to go left 3. We've already got our asymptote in there. And I got to go up 2. All right, so let's see if I can do all that at the same time. And then I'll fill in the rest of my chart here. So let's see. Let's start with, well, we'll start with our leftmost point. So if we reflect that in the x-axis, it's going to go up to positive 1. It'll be 1/2 positive 1. And then I got to go left 3, 1, 2, 3, and up 2. So let me hit that again. 1, 2, 3, 1, 2. So that point, that first point right there is going right there. That's now where the point 1 moved to. Okay, the second point, reflection, does nothing to it. Left 3, 1, 2, 3, up 2. It's going to go right there. So that's the second point. That's our second point. Here's our third point. I reflected. It's going to go down here to negative 2, and then left 3, 1, 2, 3, up 2. So it's now going to be right there where that point was. Shoot. Everybody's sitting here saying, Mr. Smarter, what about the stretch? What about the stretch? Yep, I forgot my stretch. So let me get rid of these. You know what? We all make mistakes. And the reason I'm not editing the video is because I don't know how without starting all over. So you can just speed right on through this part. Let me go here. Let me get this stretch by a factor of 4. Thank you for your patience. All right, let's try this again. Let me get this point back in here. That's key to my success. Okay, now let's try this again. Okay, if I reflect the point I've got labeled as 1, it goes up to 1. Then I've got to stretch it by a factor of 4. So 1 times 4 goes up to 4. Then I'm going left 3, 1, 2, 3, and up 2. So that's where that number 1 point should go. So sorry about that. All right, and now let's see what we have here. The point that is number 2, I'm labeling it, it's 1, 0. So if I reflect it, it goes nowhere. If I stretch it, it goes nowhere, right? Because 0 times anything is still 0. So I only have to go left 3 and up 2 here. So 1, 2, 3, 1, 2. So there's our point number 2. All right, our point I've labeled number 3. If I reflect it, it's going down here to negative 2. Stretch it by a factor of 4, it's going down to negative 8. Then left 3, 1, 2, 3, up 2. So that looks like that should be right there. And then finally, so that's our number 3 point. And here's our number 4 point. It's already up at 4. So if I reflect it, it's going to negative 4. If I, let's see, negative 4. All right, if I stretch it by a factor of 4, it goes down to 16. Wait a minute. 8, 1, 2, 3. That should be 8, 3. Wow, I have not had a successful day on this graph. That should be 8, 3, 1, 2, 3. All right, here we go. So now reflect it, it goes down to negative 3. Stretch it by a factor of 4, goes down to negative 12. But then I got to go up 2, so it's going to be down here at negative 10, and then left 3, 1, 2, 3. So, whew. All right, so here's what this graph finally is going to look like. And that is f of x equals negative 4 log base 2 of x plus 3 plus 2. All right. Okay, now let's answer the rest of these questions. Domain, of course, I can see my domain is restricted by my horizontal asymptote, which is at negative 3. So we're going negative 3 to infinity. In behavior, so our in behavior near the vertical asymptote, so I'm going to say as f of x approaches negative, no, sorry, oops. Sorry, guys. I am not, it's early in the morning. All right. As x approaches negative 3, f of x approaches infinity. And right, as x approaches, it doesn't ask for this, but as x approaches positive infinity, f of x approaches negative infinity. All right, and the range, of course, is all real numbers. All real numbers. Oh, here's the end behavior. We just did that. So it did ask us for it. Okay, and if you want to fill in these numbers, I'll jot them down here quickly for you since I sort of had a tough time getting that graph done. Negative 5/2 input gives me 6 as an output. Negative 2 gives me positive 2. Negative 1 gives me negative 2. Positive 1 gives me negative 6, and 5 gives me negative 10. So if I had plugged in those values for x, I could have graphed this thing without doing transformations, but of course it's transformations that we're trying to learn. So that's not what we did. Okay, now we learned again that the log function is simply the inverse of an exponential function. So we're going to use these properties to go further here. So we know that when we take and we do function composition with a function and its inverse, they both equal x. Hopefully you remember that from way back in the days of Unit 1. And that's how you prove that two functions are inverses of one another. So look at this special little treat that we have here. It's quite a mouthful, but so if two functions, f of x and g of x, are inverses of each other, then as I just said, if I do function composition both ways, the result will be x. So if f of x is 3 to the x power and g of x, its inverse, is log base 3 of x, then those are inverses of each other. So if I do f of g of x, it's written there, but I'll I'll just show you how it looks. So if I do f of g of x, that's going to be 3. So write 3. And then our input is now going to be g of x. So that's going to be 3 to the log base 3 of x, right? Because that's our input now. And so I know because those are inverses, that has to equal x. And likewise, if I do g of f of x, that's going to say the log base 3, and now f of x is my input of 3 to the x, and because I'm doing function composition of inverses, I know those both equal x. So therefore, I can simplify problems like these without needing my calculator. Okay, so if I've got log, remember, because you remember, since there's no little subscript here, this is 10 to the log base 10 of 2.3. So from the above information, I know that that is just 2.3. This is a case of g of f of x, so I know that this is going to be 5x. The log base 3 of 3 to the x, of course, is just going to be x. 10 to the log base 10 of 29 is 29. I hope you're getting the gist here. I'm going to write the rest of these in. If we need to talk about them when I get back, we will surely do that. This one here, let's see what we got here. We got the log base 10 of, I'm going to think of this as 10 squared to the x power. Oh, that makes that easy. It's just 2x. Okay. So log base 3, I'll do the same here. Log base 3 of 3 squared to the x. So again, 2x. And this one here, remember the natural log? You can write it as log base e if it helps you to figure that out. And I know the square root of e is e to the 1/2. So that's just going to be 1/2. Okay, hope we're feeling okay about that. But if not, again, highlight and we will certainly go over it when I get back. All right, we're in the home stretch here, guys. We're just going to use the composition of inverse functions to prove that these two functions that were given here are indeed inverses of each other. So here's f of x, here's g of x. So first thing I'm going to do is f of g of x. And what is that going to say? All right, that's going to say e, I better give myself some room here. E, so here's f of x. It's 3x minus 6. So remember, I have to put in g of x now to the input. So g of x has to go in right there. So 3, all this, 1/3 natural log of x minus 5 plus 2. And then, don't forget the minus 6. Let's see, 3. All right, whew, that's a lot. That's a handful. And then we got our plus 5 out here. All right. Oh, sorry, that's not in the exponent. Let me make that look a little bit better. So the plus 5 is out here, not part of the exponent. Whew, now we got to simplify all that. But you know, in the end, what we're hoping for is that it equals x, because that's our first step to proving that these two functions are inverses of each other. All right, so let's just start this simplification process. 3 times a third. Okay, that's just going to be 1. And so what are we going to have here? And then I got to do, oh, I got to multiply the 3 times. So that's going to be e to the natural log of x minus 5. And then the 3 times 2, that's plus 6. And then I got my minus 6 plus 5. All right. So that is e to the natural log of x minus 5 plus 5. Right, and now remember what this is. This is what we learned just a minute ago. E to the natural log of x equals x. So I know this part right here is x minus 5. And then there's my plus 5. And indeed, that does equal x. Okay, so we've done it one way. I want you to pause here, and I want you to try to do the other half that proves that these two functions are inverses, and then come back and you can check your answer with my work. All right. Hope you had good luck there. You see, I plugged in f of x. I put it in a different color in hopes that if you were having trouble seeing what's happening, my input is right here, g of f of x. This becomes my input, so it goes in right here. So you can see that's what I did. And then when I simplified all that, g of f of x does equal x, f of g of x does equal x. So those two functions are inverses. And that's what we have for today, and we will see you next time.